In this video, we're going to learn how to sketch the graph of rational functions. We'll go through an example and I'll list some steps that we can follow as we go along. In our example here, we want to graph the rational function f of x equals 2x squared plus 5x minus 3 divided by x squared minus 3x minus 4. The first thing we'll want to do is to factor the numerator and denominator of our rational function. And then, if there are any common factors, we want to cancel out those common factors. Let's start by factoring the numerator. Since we have a 2 in front of the x squared, we're going to need to factor this by grouping. So first, let's come up with two numbers that multiply to the product of the first and the last number. So we need two numbers that multiply to 2 times negative 3, which is negative 6. And our two numbers need to add up to the middle number here, the 5. So two numbers that multiply to negative 6 and add up to 5 would be negative 1 and positive 6. So what we're going to do is we're going to replace this 5x here with negative 1x and 6x. So let's rewrite our quadratic. It's 2x squared, and again, we're replacing the 5x with negative 1x plus 6x, and then we have our last term, the minus 3 at the end. So now we're going to factor this in groups. We're going to look at the first two terms as our first group and the last two terms as our second group. In our first group, between 2x squared and minus 1x, there's a common factor of x, so let's pull that out. What's left is a 2x minus 1. Now in our second group, between 6x and negative 3, there's a common factor of 3. So pulling out a factor of 3, we're left with, again, 2x minus 1. And since there's a common factor of 2x minus 1 in both of these groups, we can pull that out, so our numerator factors as x plus 3 times 2x minus 1. So our rational function is f of x equals, in the numerator, x plus 3 times 2x minus 1. And then for the denominator, if we want to factor that quadratic here, we need two numbers that multiply to negative 4 and add up to negative 3. Those two numbers are negative 4 and positive 1. So the denominator factors as x minus 4 times x plus 1. We notice here that there are no common factors, so there's nothing to cancel out. After factoring our rational function, the next thing we want to do is find and plot our x and y intercepts. To find the x-intercepts, normally for a function we set it equal to 0 and solve for x. But in the case of rational functions, all we have to do is set the numerator equal to 0 and solve for x. So here we're going to have x plus 3 times 2x minus 1 equals 0. Now, if we have a product of two things and it equals 0, that tells me that either the first factor equals 0 or the second factor equals 0. So this allows us to split this equation up into x plus 3 equals 0 and 2x minus 1 equals 0. For 2x plus 3 equals 0, we can subtract 3 from both sides to get x equals negative 3. And for 2x minus 1 equals 0, we can add 1 to both sides to get 2x equals 1, and then divide by 2, we get x equals 1/2. To find the y-intercepts for our rational function, all we have to do is plug in 0 in for x, or think about this as evaluating f of 0. Now, when we're evaluating f of 0, we can plug in x equals 0 either into our factored version or our unfactored version. Let's plug it into our unfactored version. We have 2 times 0 squared plus 5 times 0 minus 3 divided by 0 squared minus 3 times 0 minus 4. In the numerator, we end up with negative 3. In the denominator, we end up with negative 4. So simplifying this, we get 3/4 as our y-intercept. Now that we have our x and y-intercepts, let's plot them. We have the x-intercept negative 3, 0, 1/2, 0, and then the y-intercept 0, 3/4. In our next step, we want to find the wholes and vertical asymptotes for our rational function. Remember, to find the vertical asymptotes, we want to cancel out any common factor that we have in the numerator and denominator of our fraction, and then we set our denominator equal to 0 and solve for x. Now, we've already canceled out any common factors in step 1, so really all we have to do here is set the denominator equal to 0 and solve for x. Here, we'll have x minus 4 times x plus 1 equals 0. Again, we can split these factors up to get the equations x minus 4 equals 0 and x plus 1 equals 0. On the left here, add 4 to both sides to get x equals 4, and on the right, subtract 1 from both sides to get x equals negative 1. So those are my two vertical asymptotes. Remember that we get wholes in our rational function when there's an x value that makes the denominator equal to 0, but it's not a vertical asymptote. We usually get wholes when factors cancel out in the numerator and denominator. But since nothing canceled out in this rational function, we have no wholes. Let's now plot our vertical asymptotes as vertical dotted lines. We have a vertical asymptote at x equals negative 1 and also at x equals 4. Our next step is to find the horizontal asymptote or oblique asymptote for a rational function. Remember, this depends on the degrees of the polynomials in the numerator and denominator. For this example, we have 2x squared in the numerator and x squared in the denominator, so both the numerator and denominator are degree 2. When that's the case, we have a horizontal asymptote, and specifically, since the degrees are the same, we know that the horizontal asymptote is y equals the fraction of the leading coefficients. The leading coefficient in the numerator is 2, and the leading coefficient in the denominator is 1. So our horizontal asymptote is y equals 2 divided by 1, which is just 2. So what we want to do now is plot a dotted line on our graph for this horizontal asymptote. We're plotting here y equals 2. In our next step, we want to determine where our graph crosses the horizontal asymptote or oblique asymptote. In general, if you want to find the intersection of two functions, you set the functions equal to each other and you solve for x. In this case, if we want to find where the graph crosses the horizontal asymptote or oblique asymptote, we want to set our function equal to the asymptote and solve for x. So our function is 2x squared plus 5x minus 3 divided by x squared minus 3x minus 4, and we want to set this equal to our horizontal asymptote, which is y equals 2, so we set this equal to 2. Note that when I wrote down the function on the left-hand side here, I used the unfactored version for our function. It's usually easier to solve the equation if we use that version rather than the factored version. To solve this equation, we want to first get rid of the fractions by multiplying both sides by the denominator. So I'm going to multiply the left-hand side by x squared minus 3x minus 4, and multiply the right-hand side by x squared minus 3x minus 4. When I do this, on the left-hand side, this factor will cancel out with the denominator, leaving us with just the numerator 2x squared plus 5x minus 3. And on the right-hand side, 2 times x squared minus 3x minus 4 gives us 2x squared minus 6x minus 8. Notice that on either side of our equation, there's a 2x squared. So if we subtract 2x squared from both sides, that term will cancel out. Next, we can add 6x to both sides. That's going to give us 11x minus 3 equals negative 8. And then we can add 3 to both sides to get 11x equals negative 5. Then we're going to divide both sides by 11 to get x equals negative 5 over 11. So this is telling me that my function will intersect the asymptote at x equals negative 5 over 11. And what we'll want to do is we'll want to plot this on our graph. So go to x equals negative 5 over 11, which is about here. Go to our horizontal asymptote and plot our point there. So this is where my graph will cross that horizontal asymptote. Sometimes when you set your function equal to your asymptote, you'll end up with no solutions. And when that's the case, it means that your graph does not cross your asymptote. Our next step is to make a sign chart for our function. Let's start by drawing a number line. On our number line, we want to divide it according to the x values where our graph might have a sign change. And those are the x-intercepts and the vertical asymptotes. So we have an x-intercept at negative 3, a vertical asymptote at negative 1, another x-intercept at 1/2, and then lastly another vertical asymptote at x equals 4. So our number line is divided into 5 different intervals. We want to determine the sign of our function on each of these intervals. To do that, We pick an x value in that interval, we plug it into our function and see what sign the output is. Let's start with this first interval here. The x value is less than -3. For example, you can pick something like -4. We want to determine the sign of f of -4. One thing you can do is plug this input into the factored version of the function. This gives us -4 plus 3 times 2 times -4 minus 1 divided by -4 minus 4 times -4 plus 1. Now, if you want, you can type this into your calculator and see what the exact output is and see if it's positive or negative. An alternative is to just determine the sign of each of the factors that we have here. For example, the factor -4 plus 3, we know that that's going to be negative, so I'm going to highlight that in red. The factor 2 times -4 minus 1 is also negative, so I'll highlight it in red. The factor -4 minus 4, again, that's negative, so highlight that in red. And then the factor -4 plus 1, that's also negative. Let's highlight that in red. Now, if I multiply out two negative factors in the numerator, that's going to turn the numerator positive. And multiplying two negative factors in the denominator will turn the denominator positive. So if I have a positive number divided by another positive number, I know that the overall result is going to be positive. So just by determining the signs of each of the factors, we can determine the sign of the output without actually finding the exact value of the output. So we now know that if we plug in an x value less than -3 into our function, the output is going to be positive. So we're going to draw a plus sign on top of that interval on my sign chart. Next, we have the x values from -3 to -1. Here, we can pick an x value like -2. So let's look at f of -2, plug that into our function. We have -2 plus 3 times 2 times -2 minus 1 divided by -2 minus 4 and -2 plus 1. Once again, let's determine the sign of each of our factors. -2 plus 3, that's going to be positive, so let's highlight that factor in green. 2 times -2 minus 1, that's negative, so I'll highlight it in red. -2 minus 4 is negative, so highlight that in red. -2 plus 1 is also negative, so we'll highlight that in red as well. Now in the numerator, we have a positive factor times a negative factor, so our numerator is negative. In the denominator, we have a negative factor times a negative factor, so the denominator is positive. A negative number divided by a positive number is negative, so overall the sign of my output is negative. So for x values between -3 and -1, we know that our function is negative. So we draw a minus sign above that interval on my sign chart. For our next interval, for x values from -1 to 1/2, we can pick an x value like x equals 0. We've already evaluated f of 0 when we found the y-intercept. We saw that the output was 3/4, which is a positive number, so we're going to draw a plus sign on my sign chart. So next, we have the interval from 1/2 to 4. We can pick an x value like 1 on this interval. Evaluate f of 1. We have the factors 1 plus 3, then 2 times 1 minus 1 divided by 1 minus 4 times 1 plus 1. Let's figure out the sign of each of our factors. 1 plus 3 is positive. 2 times 1 minus 1 is positive. 1 minus 4 is negative. And then lastly, 1 plus 1 is positive. In the numerator, we have a positive factor times a positive factor, so overall the numerator is positive. In the denominator, we have a negative factor times a positive factor, so overall the denominator is negative. And we have a positive number divided by a negative number, so overall the function's output is negative there. So for the interval from x equals 1/2 to x equals 4, our outputs are going to be negative. We just have one last interval for our sign chart, x values greater than 4. So for example, we can pick something like x equals 5. Looking at f of 5, we have the factors 5 plus 3 times 2 times 5 minus 1 divided by 5 minus 4 times 5 plus 1. 5 plus 3 is positive, 2 times 5 minus 1 is positive, 5 minus 4 is positive, and 5 plus 1 is positive. Since all of the factors are positive, we know that the overall sign of our function is going to be positive there. So for the interval for x values greater than 4, we know that our function is positive. So now we've completed our sign chart. Now this is optional, but one thing you can do is indicate on your graph where your function is positive and negative. So for the x values less than -3, I know that my function is going to be positive, so I'm going to highlight this region of my x-axis in green. Next, for x values from -3 to 1, my function is negative, so I'll highlight this part of my x-axis in red. Then from -1 to 1/2, my function is going to be positive. Then from 1/2 to 4, my function is going to be negative. And then lastly, on the interval from 4 to infinity, my function is positive. Seeing the colors on my x-axis here will tell me whether my graph will be positive or negative, which means that when I draw the graph, it'll tell me whether it's going to be above the x-axis or below the x-axis. So our last step here is to use all of our information to draw a sketch of our graph. When we're drawing our graph, we're basically deciding what happens at each asymptote, and then we're also connecting all of the points that we have there already together. Usually, what I like to do is work my way from the left to the right. So in the very leftmost portion of this graph, we have the horizontal asymptote. Now, the graph can do two things. It can either go towards the horizontal asymptote from above, or it can go towards the horizontal asymptote from below. Now, keep in mind that as we go from left to right, the next thing my graph needs to connect to is this x-intercept here. So if my graph goes towards the horizontal asymptote from above, it would look something like this. And if it goes towards the horizontal asymptote from below, it would look something like this. Now, to help us decide which is the correct behavior, we want to go back and think about what happened in step 5. In step 5, we determined where the graph intersected the horizontal asymptote or oblique asymptote. In this case, we found that the intersection was at x equals -5/11, which is this point over here. The graph does not intersect the horizontal asymptote anywhere else. Specifically, there's no crossings anywhere on this region of the graph. So this tells me that my graph isn't going towards the horizontal asymptote from above, it's going towards the horizontal asymptote from below. So I would draw something like this. Now, as we make our way to the right, we see that our next big feature is this vertical asymptote here, specifically the left-hand side of this vertical asymptote. Again, there's going to be two options for the graph's behavior. The graph can either go up to infinity or it goes down to -infinity. When deciding the behavior at a vertical asymptote, we can always use the sign chart to help us make that decision. Now, on the interval from -3 to -1, we see that our graph is negative there. And so my graph has to be below the x-axis. It can't be above the x-axis. So it has to go down to -infinity. So let's draw our graph going down. If we keep going to the right, the next big feature is the other side of the vertical asymptote. On the other side of the vertical asymptote, my graph can either go up to +infinity or it goes down to -infinity. Again, we can make our decision using our sign chart. We see that on the interval from -1 to 1/2, our graph is positive there, which means it has to be above the x-axis. So my graph has to go up to +infinity here. Drawing that and connecting it with some of the points that we have, we get the following graph. Now that we're at this x-intercept, if we keep going to the right, our next big feature is this vertical asymptote. At the vertical asymptote, there are again two choices. The graph can either go up to +infinity or it goes down to -infinity. According to our sign chart, for x values between 1/2 and 4, our function is negative there. So the graph that I draw should be below the x-axis. So let's draw our graph going towards -infinity as we get closer and closer to that vertical asymptote. Next, we have the other side of the vertical asymptote. The graph can either go up to +infinity or it can go down to -infinity. Again, at vertical asymptotes, we can decide on what happens using the sign chart. For x values from 4 to infinity, our sign is positive, so we have to draw our function above the x-axis. That's why the graph has to go up to +infinity. So let's draw a segment going up. And as we make our way to the right, our last feature is this horizontal asymptote on the right here. Our graph again has two behaviors. It can either go towards the horizontal asymptote from above, or it goes towards the horizontal asymptote from below. To help us decide what the behavior is, we again think about what happened in step 5. We saw that the graph crosses the horizontal asymptote at x equals -5/11, which is right here. It does not cross the graph anywhere else. So specifically, there's no crossing over here on this side of the graph, which means that my graph has to go towards the horizontal asymptote from above. So let's finish off our graph, drawing our graph going towards the horizontal asymptote from above. So this is how we use all of the information that we've obtained to help us draw the graph. So let's quickly go over the steps of graphing a rational function again. We factored the numerator and denominator. We found the x and y intercepts. We found the holes and vertical asymptotes for our function. We found the horizontal or oblique asymptotes for our rational function. And then we determine where our graph crosses the horizontal or oblique asymptote. After that, we make a sign chart for our function, and then we use all of that information to help us draw the graph. So that's it for this video. In our next video, we'll go through another example of graphing a rational function.